work done by a constant force. So far what we've seen is the work done by a constant force, a force that remains fixed in direction and magnitude both, is given by the relation F is equal to F dot S, scalar product with uh, displacement. Okay. Now, next thing we'll see is work done by a variable force. So if a force is changing either in magnitude or direction while the displacement is happening, okay, it is called a variable force. So if either the magnitude or variable or the direction of a force is changing, okay, so it's basically magnitude or direction, or both of the things can also happen. So when we say or direction, we can say and or. While the body it acts on is displacing, then the work done by that force is defined by this relation. Integration of F dot ds from initial to final position, okay, where ds is a very small displacement, okay, or you can think of that like a displacement during a very small time dt. Okay. And therefore work is defined as what we call the path integration of force, okay, from the initial to the final location. Okay, so that's ds, and of course F over here is the instantaneous value of force during the displacement ds. So at the moment when that very small displacement is happening, whatever the instantaneous value is, that is the value of F in the integration. So just make a note of this. We will continue from this. All right, so next let's understand this with an example. Now the most obvious example of this is like the work done by spring force, because the spring force, as you know, varies. Okay. Okay. So let's say what we're doing here is a spring is attached to a wall on one side and block on the other side. Let's say what we have here is a frictionless surface. It's a smooth surface. So this is a spring or spring constant K. Okay. So this is initially at the natural length position. So an ideal spring or spring constant K and natural length L is attached to the block. Okay. Now what we do is we apply an external force to pull the block from this position to eventually this new position, which I'll show below. So we want to extend the spring by pulling the block through a certain distance. Now let's say the spring is getting extended by a certain distance d. So you can see that the block has been displaced by that same distance d. So in the process, what is happening? We know that the spring develops a tension now, develops a tension of, so we can just say that there is spring force or tension acting in the spring like this. So an external agent pulls the block through a distance of d, let's say. Okay. So we want to, so given the values, suppose spring constant is given to us as say 20 newtons per centimeter. Okay. Natural length is, let's say, 10 centimeters. And the distance through which we are pulling it is, let's say, 2 centimeters. So we want to find the work done by the spring force on the block. So just take down the data of the question. I'll explain to you next how to work this out. Yes, that's correct. So we'll have to use that. The spring force is variable. So we have to integrate. Okay. So the first thing here is that the spring force is variable because its magnitude is kx, where x is the extension, okay, and its direction is opposite to the displacement. Okay, so you can see that this is a variable magnitude. So we will use the integration method. Okay. However, this is going to be a one-dimensional example. So what will happen is that the dot product will just result in simple product. Okay. So at some intermediate time, let's say the extension of the spring is x. Okay. So x is right now less than d, but greater than 0. So the spring force that is acting on the block, that spring force has a magnitude of kx. Okay. Or if I take my xy axis like this, I can write the spring force as minus kx I cap. Is acting along the negative x direction. Okay. Now, very small time later, say the block makes a displacement like this. So this is my dx. Okay. Because now this has become L plus x plus dx. Okay. So the differential displacement will be dx I cap. This is the small displacement. The small time dt. Okay. So work done by my spring during that small displacement, that is becoming minus kx dx. When you take dot product of this and this, you can see here it becomes minus kx dx. Okay. So total work done by spring is integration of this. So it is integration of f dot ds, which is simply becoming integration of minus kx dx from the initial to the final. So the initial state was what? X equal to 0. And the final state is x equal to that distance d. So now this integration has to be carried out. Okay. So next step will be very simple. The integration will come to that, but note down up to here first. Yeah, very good. So now you substitute the values. Okay. Spring constant K is given and the distance D is given. So you got the answer correct parametrically. Now just put the values. Okay. K was 20 newtons per centimeter. Okay. And the final extension D is 2 centimeters. So you can tell me how much the work done will be in joules. You know? So it should be 0.4 joules. No, no. See the unit better. It's centimeters. You know? Yeah. So 0.4 joules. Okay. So let's look at this integration. It's very simple. Minus K will come out. X dx integrated from x equal to 0 to x equal to d. So x dx integration is x square by 2. Now put the limit 0 to d. So it will be minus kd square by 2. So that is the work done parametrically. So now just substitute the values. So it is 20 into, sorry, half of minus half into k. Now k is 20 into 10 raised power 2. If you substitute in newtons per meter. Okay, into d square, that is 2 into 10 raised power minus 2 whole square. You substitute this in meters. Okay. So we will get it as minus 0.4 Newton meter. Newton meter is the same thing as joules. So the work done by the spring will become minus 0.4 joules. It's easy to understand why it's doing negative work, because the direction of the spring force is opposite to the direction of displacement of the block. Okay. But the value is going to come from integration and not from simple dot product. Okay, very good. So let's move on to another example of work done by variable force. So now let's say we have this situation where a block of mass m is lying on a rough surface which has coefficient of friction 0.1. Mass of the block is given to us as 10 kgs. G as 10 meters per second square. Okay. Now the block is at the x coordinate x equal to 1 initially at rest. Okay. This is my origin, this is my x-axis. And now what we do is we start applying an external force like this, but that force is going to be variable. Okay. And as a result of that, the block reaches the position x equal to 5 after some time. By then it has a speed v. Okay. So a variable force of magnitude F is equal to 20 by x square. Let's make it 200 by x square, where F is in newtons and x is the x coordinate in meters. So this kind of variable force acts on the block shown horizontally. Okay. Find the work done by the force F as the block moves from the position x equal to 1 meter to the position x equal to 5 meter. And secondly, find V at x equal to 5 meters for the block. What is the speed of the block when it reaches x equal to 5 meters? So just try this question out, we'll discuss. गुड मॉर्निंग मैम। मैम मैंने आपका नंबर ज्ञानेश्वर सर से शेयर किया है, जो हमारे केमिस्ट्री टीचर है ना, सीनियर मोस्ट। ही विल बी इन टच विथ यू टुडे मैम, कि वो इलेक्ट्रोकेमिस्ट्री का जो लेक्चर है
कभी भी सर, जब भी उसके पास टाइम हो, आधा घंटे का 1 घंटे का, जब भी टाइम हो, बस
हाँ
थोड़ा
हाँ
सा उसको हेल्प कर दीजिए।
नहीं, और आई थिंक वो क्या कर रहे हैं ना, लाइक 12th का भी अपना रिवीजन चल रहा है ना,
अच्छा,
सो ही विल बी प्रॉब्ली टेकिंग वन फुल सेशन, और उसमें वो प्रॉब्लम्स का शीट वगैरह भी रहेगा, तो वो सेशन भी अगर वो अटेंड कर सकता है ना, तो वो भी बहुत अच्छा रहेगा।
ठीक है सर, फिर वो जैसा भी सर बोलेंगे मैं
हाँ
मेरे
हाँ
बेटे से बात करा दूंगी।
हाँ हाँ, मैं उनका नंबर भी फॉरवर्ड कर देता हूँ, बट ही आस्क्ड फॉर योर नंबर, तो मैंने उनको भेज दिया, सो ही विल कॉल यू टुडे सम पॉइंट इन टाइम।
इवन बेटर सर, कुछ जब ऐसा कर लेंगे, मैं करूंगी तो हो सकता है शायद वो डिस्टर्ब हो जाए।
नहीं नहीं, ऐसा कुछ नहीं है, मतलब मैं जस्ट कहा कि आप नंबर रख लीजिए, इनकेस आपको यू कैन सेव द नंबर।
ठीक है सर, ये भी ठीक है।
या
कॉल करेंगे तो एटलीस्ट मुझे पता रहेगा कि
हाँ
सर
हाँ
कॉल
हाँ,
करते हैं।
ही विल कॉल यू टुडे, ओके मैम।
सर आपने यहाँ पे मुझे आपसे एक बात और करनी थी
हाँ
कि सर हीरा ना
Okay, so let's see how to calculate the work done. So first part, W is equal to F dot ds का integration. Now यहाँ पे see what is happening. The force is acting along the x-axis. It has a magnitude of 200 by x square, and the small displacement will also be along the x-axis only. Okay, so this will just become 200 by x square into dx, because the angle between the force and the displacement is 0, so cos 0. So magnitude of force into dx. And now we have to integrate this from initial to final. So that is x equal to 1, so x equal to 5, right? So now you know that this integration, okay, you know that what is the integration of dx by x square? It is integration of this. So just use the formula x to the power n's integration is x to the power n minus 1 plus upon n minus 1 plus c. So it's minus 1 by x. That's the indefinite integration. So this is what we will use over here. So this will become 200 into minus 1 by x, limits 1 to 5. So that is 200 into minus 1 by 5 minus of minus 1. So that will become 200 into 1 minus 1 by 5. ये होगा ना? So 4/5 of 200, that will be the work done in joules. That's how much now? 160 joules. That is the work done by the force F. Okay, that's the first part. So I don't know, some of you did not get the answer correct. So make sure you understand the process properly. Maybe you did the integration wrong, I'm not sure. Just check. Okay. Now for the second part, we will use work kinetic energy theorem. That is, the net work done by all the forces should be equal to the change in kinetic energy. So we will use that formula and that theorem. So here we'll need to calculate the work done by friction. Okay. Because friction will also be doing work. Okay, so hope you've understood this part. Now for the second part, what you do is you calculate the work done by friction, so that you can calculate the net work done then, because we'll use the work kinetic energy theorem. Okay. That also we discussed about last time. Concept of work kinetic energy theorem, that the net work done is equal to the change in kinetic energy. So this net work done is the algebraic sum of work done by all forces on a body, that equals to the change in kinetic energy. And change in kinetic energy, of course, is half m into final speed square minus half m into initial speed square. Okay, so next part, let's understand what's happening is all the forces, if you see now acting on this block, there is all this acting together. There is, apart from this external force, there is kinetic friction, normal reaction, and mg acting. And the displacement of the block is like this. From x equal to 1 position to x equal to 5 meters position. So the displacement is 4 meters along the positive x direction. Like this. Okay. So here F is a variable force. Okay. So we calculated work done by F by integration method, and we got that. वो तो आ चुका है. We have got that as whatever it was, 160 joules. Okay, but the other forces, work done by mg will be 0. Work done by normal reaction will be 0 because mg acts perpendicular to displacement. Normal reaction acts perpendicular to displacement. And what about work done by friction? That will be minus F into S, because friction has constant magnitude and direction opposite to the displacement. Okay, so now the magnitude of friction you can see will be mu n, so that will be mu mg. Okay, so that will be 0.1 into 100 newtons, so 10 newtons. That is the magnitude of friction. So this will become minus of 10 newtons multiplied by 5 meters. So friction is doing a work of this much now, minus 50 joules. This is the work done by friction. Okay. So next thing we'll see that the net work done is equal to change in kinetic energy. So work done by F plus work done by friction plus these two is 0 anyway. So this should be equal to half mv square, because the initial speed here was 0. At the starting point, the speed was 0, so the kinetic energy is 0. And v at this point, we want to calculate how much it is. So, okay, so this will be plus 160 minus 50. The other two are 0. This should be equal to half into 10 into v square. So v you can see will become, this is going to be 110. So 11, so square root of 22. meters per second. So this should become the answer. Okay, so just make a note of this, people. Okay, people, so hope you're done with this question and understood this. Now, next, we will understand a very important concept related to forces. Okay, and that is about the work done by the force, the nature of the formula of the work done. Okay, especially it applies to variable forces, and that is called the classification of forces into conservative and non-conservative forces. So let's understand this definition next. So we've seen that in general, the work done by a force is defined as integration F dot ds in general. Okay, or this reduces to a special formula F dot s for a constant force. Okay, so what happens is that in certain cases, the work done by the force will depend only on the initial and final position, and it will not be a function of the path taken from initial to final. So in such cases, we say that the force is conservative because the work done is what we say independent of path. No, it's a path integration function. It's a path independent function, and it depends only on the final position and the initial position. It doesn't matter what route or what path we take from initial to final. So if that is the case, then we say that the force is conservative. Whereas in other cases, it can happen that the work done by the force actually depends on what path we have taken from the initial to final. So between the same 2 points, if we take two different paths, the work done by that force will come out to be two different values. So when that happens, we say that the force is non-conservative. Okay, so that's how the definition of conservative and non-conservative works out. Now you'll understand this better when we look at the example based on this also, okay, for each type. But let's start by understanding the definition. So as I said, a conservative force is one such that the work done is independent of path. So it should be independent of the path, okay, and depends only on the initial and final position. Then the force is defined to be a conservative force. That's the meaning of the term conservative. Okay. One example of this is any constant force. Any constant force. Okay. The work done is F dot S. So you can see that it is path independent. I'll show you with a numerical example also next, but first note down this definition. Okay. So for example, gravitational force. or what we call the weight of a body at the Earth's surface. Of course, we're talking about that. It's a constant force. So let's look in this example at two situations. One, we have an irregular slope between the point A and the point B. And this height is, let's say, 20 meters, and this distance on this side is 50 meters. And we have this situation on the one hand, okay, and on the other hand, we have a situation where we have a different path, but between the same initial position A and the final position B. This, okay. So a particle of mass m slides down a surface from the point A to B. In both cases, 1 and 2. Okay, we have to find the work done by the gravitational force. So we'll see that there are two different paths as the body is moving. One path is like this. One path is like this. But the work done will not depend on that. It will only depend on the, because it's a dot product now of the force and displacement. So we'll see that work done by mg will be mg dot s. No? And in both cases, the displacement from A to B is going to be, if I take x and y axis like this, it's going to be minus 50 I cap, minus 20 j cap. And the gravitational force is going to be, its mass is 2 kg, so minus 20 j cap in newtons. This is in meters. So in both the cases, we'll see, will be 1000 joules. Second case also it will be 1000 joules. So showing you that it's independent of path. It only depends on the position, the initial and final position. So I'm taking the same pair of initial and final position, but two different paths. But the work done by gravity is coming out to be the same in both. Why? Because it's a constant force in this case. So gravity becomes which type of force overall? It becomes what we call a conservative force. Okay, so the conclusion at the end over here is that the work done is the same even though the paths are different. For displacement from A to B by two different paths. Okay. Because weight or gravitational force is conservative by nature. Now, once we understood this, let's come to the definition of non-conservative force. If the work done by a force depends on the path taken from initial to final, that means for two different paths between the same initial and final position, we get two different values of work done in joules. Okay, then such a force is non-conservative. So if the work done by a force is what we call path dependent. Now that one it was independent, this one is path dependent. Then the force is defined as a non-conservative force. Okay, so the work done, so for such a force, the work done by two different paths from the same initial to final position will be different. That is the thing. So the best example of this is kinetic friction. And once again, I will show you with a numerical example how this happens for kinetic friction. Okay, so let's visualize a situation like this. We have on a horizontal plane so this is a now we are taking a particle from this position A to this position B via two different paths. In one case, we are taking it by a direct path like this, and in another case, we are taking it by two different paths like this. Okay, so if I draw the diagram in the XY plane now, the same thing is looking like this. This is my second path, this is my first path. Okay. So let us say this is okay. So this has a coefficient of friction 0.2. Now a particle of mass 20 kg is moved from A to B on the rough horizontal surface by two different paths. Okay. So you want to calculate the work done by kinetic friction in each path. Okay. So just take down the question. I'll explain to you how this is done. Okay. So now see what's happening is that when we are going in path 1, for the body's displacement in this direction, the frictional force will be in this direction, and the total distance from A to B will become 7.5 meters. So for path 1, the work done by friction will be minus of kinetic friction into S, okay, where kinetic friction's value is mu mg. So that is, we're taking the coefficient of friction to be 0.2 to 20 kg block. So 40 newtons, okay. But more importantly, the distance through which it is moving is 7.5 meters. So this will become minus of 40 into 7.5. This will be the work done by friction. Now for the second part that you can see now, for path 2, okay, the work done by friction, we'll have to calculate like this. When it's going here, the displacement is like this, and the kinetic friction acting is like this. So we'll take this distance as S1. Okay. But when it's going here, the displacement is in this direction, the kinetic friction is like this. So we'll take this as S2. So the work done we'll have to calculate in two parts. Minus of kinetic friction into S1, and again minus of kinetic friction into S2. So this will become minus 40 newtons, okay, into 6 meters. And then again minus of 40 newtons into 1.5. Sorry, this was not 1.5, this was 4.5. Let's make a correction here. This is not 1.5. This should be 4.5 meters. That's how the hypotenuse will come out to be 7.5 meters. This angle here is 90. So you can see the work done by friction for the second path is different than the work done by the friction for the first path. So friction is acting like a non-conservative force. Okay, people. So hope you've understood this example. Now today's session will conclude a little bit early here because you have another session coming up at 12, some board lecture coming up at 12. So just take a 15-minute break before you can start that lecture. Okay. So that's it for today's session here. Wish you all the best. Next time we will continue with this concept of conservative and non-conservative forces, and from that we will discuss about potential energy and work energy theorem. Okay. So that's it for today, people. Wish you all the best. You have a lecture at 12 o'clock for boards. I'm sure you're aware, right? So that's it for today. Okay, good.